I'm walking around my neighborhood in Austin when I spot an advertisement on the back of a U-Haul truck. Now, U-Haul isn't exactly synonymous with aerodynamics, but their bold claim catches my eye, and I decide to put it to the ultimate test. Forget moving furniture across town. I'm going to see if I can make a U-Haul go hypersonic. Not the actual truck, mind you, but a scale model of one tested in a hypersonic wind tunnel. Depending on how things go, we might even set this model loose in an empty test section to see if it's dynamically stable at Mach 7. This might just be the most ridiculous experiment I've ever attempted. So I head to the University of Texas at San Antonio, about 2 hours south of Austin, where they have a rare piece of equipment, a hypersonic wind tunnel. It's managed by Dr. Chris Combs, who you might know as the laser-eyed hypersonic professor on Twitter. Dr. Combs uses this tunnel to test control mechanisms for hypersonic vehicles traveling in the upper atmosphere. He explains the challenge: at high altitudes, control surfaces like flaps and fins become ineffective because there's not enough air density to generate aerodynamic forces. Instead, hypersonic vehicles rely on control jets, like the reaction control systems, RCS, used on the space shuttle. But there's a tricky middle ground where the atmosphere is thin enough to render flaps useless, yet dense enough for hypersonic airflow to interact with those jets. This can cause unpredictable effects, sometimes even making the vehicle move in the opposite direction of the jet's thrust, a major problem for the new wave of hypersonic aircraft being developed. You might be surprised to learn that intercontinental ballistic missiles, ICBMs, travel much faster than hypersonic vehicles, reaching speeds of up to 7.8 kilometers per second. ICBMs exit the Earth's atmosphere, travel through space, and dive toward their targets. Their high, arcing trajectory gives enemies more time to detect and counter them with anti-missile defenses. Hypersonic missiles, on the other hand, cruise within the atmosphere at about half the speed of an ICBM. The atmosphere slows them down, but their low-altitude flight path keeps them hidden behind the Earth's curvature until the last moment, giving targets minimal time to react. This makes hypersonic wind tunnels critical for companies and government agencies developing these vehicles. And today, we're using this cutting-edge tool to test a vehicle designed for moving couches, not missiles, a U-Haul model. We're setting up the test, mounting the U-Haul model to face the airflow in the tunnel. I jokingly ask if we should test it in reverse, but we stick with the forward orientation for now. The model, a collector's item with an original price tag of $7, though I snagged it for $40, is carefully unboxed. Somewhere, a U-Haul model enthusiast is probably cringing. We mount it on a variable angle of attack strut, which still has a cow figurine attached from a previous test apparently, groundbreaking bovine aerodynamics research. The plan is to secure the U-Haul model to this strut, which has a quarter-20 thread, and subject it to Mach 7 airflow. So how does this wind tunnel achieve such extreme speeds? On one end, there's a massive vacuum chamber, and on the other, a pressurized tube. They're separated by a metal diaphragm designed to burst at a specific pressure differential. You'd think increasing the pressure would boost the airspeed, but it's not that simple. Dr. Combs explains that the Mach number 7.2 in this case is fixed by the tunnel's geometry, specifically the shape of the nozzle. This nozzle works like a rocket nozzle, accelerating air from subsonic to supersonic speeds. In the converging section, air speeds up to Mach 1 at the throat, and then, as the nozzle diverges, the air expands and accelerates further, much like cars spreading out when a highway adds lanes. Increasing pressure only affects the Reynolds number, mass flux, and equivalent altitude, not the Mach number. To prevent the air from freezing in the test section, the tunnel is equipped with electric heaters wrapped around the pipe, insulated to keep the heat in and protect anyone nearby. The air is heated to around 700 Kelvin, about 800 degrees Fahrenheit, to keep it above the liquefaction point. Without this, the extreme expansion in the nozzle would sap so much energy from the air that it could condense into liquid, skewing the test results. Even at 700 Kelvin, this is still a cold tunnel compared to true flight conditions, which would require heating to 2000 Kelvin beyond the limits of the stainless steel components. Only a few specialized facilities can simulate those conditions. The tunnel's design maximizes test duration by using a long pressurized tube, allowing a longer column of air to flow through. Though the test happens in a fraction of a second, high-speed cameras capture detailed data. But as we prepare to pressurize the system, we hit a snag. The pressure gauges start glitching, which is a problem because they trigger the camera's recording. Without a working trigger box, we'd have to manually start the camera within a 1-second buffer when the diaphragm bursts. With only 40 minutes until the test, Eli, one of the team members, scrambles to diagnose the issue. It's a short circuit somewhere in the system. We unplug components one by one until we isolate the culprit, a faulty microcontroller board. Replacing it solves the problem, and we're back on track. With the technical issues resolved, we lock down the lab for safety. I learned that the laser bell, I'd imagined as some sci-fi contraption, is just a regular bell to warn nearby labs about laser-use lasers that could, as Dr. Combs puts it, blind the heck out of you. As we wait for the pressure differential to build, there's a moment of tension. If the diaphragm doesn't burst at the expected 300 psi, we could hit 320 psi, and I'm not sure our little plastic U-Haul can handle that. Finally, the diaphragm burst, not with the dramatic boom I expected, but with a prolonged metallic hiss, like a giant metallic fart. We stop the airflow, turn off the vacuum pump, and head outside to review the high-speed footage. The footage is thrilling. The U-Haul model, subjected to Mach 7 airflow, generates bow shock waves that create complex interactions. In the static test, where the model is fixed in place, the cab vibrates wildly, but the fact that this plastic toy survives a hypersonic blast is impressive. When we test it at an angle, it starts to tip downward, catching more airflow under the hood, nearly achieving stable flight. Dr. Combs sums it up, "I don't know what we learned, but I'm excited." The viewing window is small, but the data gives us a glimpse into how a hypersonic U-Haul might behave. Spoiler, not well. To visualize this absurdity on a grand scale, our animator Eli creates an artistic depiction of a full-size hypersonic U-Haul test. It's a glorious blend of science and silliness. So, what did we learn? Dr. Chris Combs is a blast to work with, hypersonic wind tunnels are incredible, and U-Hauls are definitely not built for Mach 7. As for the model's fate, it might end up in the vacuum tank's graveyard of test models, waiting for an undergrad to fish it out. Dr. Combs jokes about sending misbehaving grad students in there too, recalling a conversation with the tank's manufacturer about adding access flanges big enough for a student's arm. For those wanting more, I've uploaded an uncut 27-minute tour of the wind tunnel to Nebula, packed with moments we couldn't fit into this video. Nebula lets us share in-depth content without worrying about YouTube's fast-paced algorithm. On YouTube, I've learned to streamline explanations, like skipping detailed breakdowns of equations, which used to lose half the audience. On Nebula, we can dive deeper for fans who love the nitty-gritty. You can access this and other exclusive content, like our Logistics of D-Day series or videos on Japan's maglev trains, for just $2.50 a month. It supports our team and lets us push the boundaries of educational content. Plus, you get early, ad-free access to videos like this one, which has been on Nebula for over 2 weeks already. So, if you're into engineering and don't mind a slower, more detailed pace, check it out. And no, this video is definitely not sponsored by U-Haul.